Welcome back, everyone. In this lecture, we introduce function transformation. Before we talk about function transformation, we need to be familiar with graph of, let's say, some toolkit functions. These are the functions that we will use for examples, and we will apply the transformation rules to these toolkit functions in order to be able to transform them. So I encourage you to make yourself familiar with these 9 basic parent functions or toolkit functions. There is constant function, a linear function, which is f of x equals x, the absolute value function, f of x equals absolute value of x, the quadratic function, f of x equals x squared, cubic function, f of x equals x cubed, the square root function, f of x equals square root of x, cube root function, f of x equals cube root of x, reciprocal function, f of x equals 1 over x, and the reciprocal squared, 1 over x squared. We will use some of these toolkit functions and we will apply the transformation rules in order to make some other functions and some other graphs. We will come back to each of these type of functions at different chapters of your textbook, and we will talk about them in more depth, about the domain, range, and the properties, detailed graphing. But for now, we just need to be familiar with the basic graphs. So, what is function transformation and how do we use them? We basically begin with these parent functions that we just talked about, and we may shift these parent functions to right or left, up or down. We may stretch or compress them, reflect them in the x-axis or in the y-axis, and we will be able to get more graphs, and we will be able to get the functions by applying changes to the parent formulas. So we will talk about all these details. First, I would like to focus on a vertical transformation. I'm referring to the transformations which will affect f of x, the y coordinate. So any shift, any stretch or reflection, they will all be vertical and they all apply to the y coordinate. Starting with the vertical shift. Given the graph of f, assuming that a is a positive constant, we will be able to sketch the graph of f of x plus a by shifting the graph of f up a units. And we will be able to sketch the graph of f of x minus a by shifting the graph of f down a units. Vertical stretch. Suppose c is a positive constant. We will be able to sketch the graph of c times f of x by vertically stretching the graph of f by a factor of c. Now, what does that mean? In practice, we will multiply all the y coordinates by c. Now, in the case where c is greater than 1, this will actually become a vertical stretch. But in the case where c is less than 1, this will be a compression. You will see the graph of f being squeezed in this case. Vertical reflection. So if you're trying to sketch the graph of negative times f of x, you can get that by reflecting the graph of f in the x-axis. That basically means all the y coordinates being multiplied by -1. What is the proper order for the vertical transformations? The proper order for the vertical transformation is the same as order of operation. So first, we will apply the vertical stretch and reflection in any order you like for these two. And next, we apply the vertical shift, up or down. So let me use an app to show you an example where we apply these vertical transformations and see how the graph of f of x will be transformed. I would like to use the graph of f of x equals x squared, the quadratic, as the parent function. Now, I would like to show you the vertical shift. We would like to try, let's say, f of x equals x squared plus 1. You can see that the graph of f of x equals x squared is now shifted up 1 unit. F of x equals x squared plus 2, shifted up 2 units. F of x equals x squared minus 1, shifted down 1 unit. F of x equals x squared minus 2, shifted down 2 units. Let's take a look at the vertical stretch. F of x equals 2 times x squared, vertically stretched by a factor of 2. As you can see, all the y coordinates are now multiplied by 2. So the graph of f of x equals x squared now looks taller. Let's also try for some value of c less than 1. Let's say f of x equals half times x squared. So all y coordinates times half. You can see that the graph of the function now looks more flat compared to the graph of f of x equals x squared. Let's also look at reflection. Let's take a look at the graph of f of x equals negative x squared, which is reflected upside down, reflected in the x-axis. Now let's take a look at a combination. So let's say it is reflected and also stretched, and it is also shifted. So now the graph of x squared, reflected upside down, stretched by a factor of 2, so it's taller, and is shifted up 1 unit. Let's go back to our notes. Let's do an example together. The graph of f of x is given. We would like to sketch the graph of g. G is defined as 2 times f of x minus 1. So 2 times f of x minus 1. 2 means we need to apply a vertical stretch by 2. Means all the y coordinates times 2. And minus 1 means shift down 1 unit. In this order, first we stretch and then we shift. Okay, let's apply this step by step. So first I'm going to stretch the graph of f vertically by a factor of 2, all y coordinates times 2. So this y coordinate currently is negative 2 times 2 will become negative 4. This y coordinate is 0 times 2 will remain 0. This y coordinate is 4 times 2 will become 8. I'll try to maintain the general shape of the graph, vertically stretched by a factor of 2. What I see here is 2 times f of x. Now I need to shift it down 1 unit. So shift down 1 unit, y coordinate 8 will go down to 7. Y coordinate 0 will go down to negative 1. Y coordinate negative 4 will go down to negative 5. Everything shifted down 1 unit. And now we can see the graph of 2 times f of x minus 1. What is the domain of this function? Domain of g. The domain of the function didn't change. We didn't make any changes to the x coordinate. Only the y coordinate changed. So domain remains the same as domain of f. As you can see, begins with negative 5 closed all the way to open 4. The range, however, has changed. Range of g begins from negative 5 open all the way to 7 closed. Let's take a look at another example. We would like to see what type of transformations we need to apply to f of x equals absolute value of x to get the graph of g of x equals negative 3 times absolute value of x plus 2 in the correct order. Negative 3 times absolute value of x plus 2. Same as order of operations. We can see that we have a vertical reflection, negative. Vertical reflection, which is basically reflection in the x-axis. We also see a vertical stretch by a factor of 3. And finally, we need to apply a vertical shift up 2 units. And what is the correct order? The stretch and reflection could be done in any order. The shift needs to be done at the end. Why don't we use our app to take a look at the graph of this function? So we have the absolute value. Let me set everything back to 0. Absolute value. Here's the graph of f of x equals absolute value of x. Now we would like to look at negative 3 times absolute value of x. Negative 3 times absolute value of x plus 2 plus 1 plus 2. It is vertically stretched, reflected, and then shifted up 2 units. Now let's talk about horizontal transformations. Horizontal transformations are the ones which affect x. Starting with the horizontal shift. Suppose a graph of f is given and b is a positive number, and you're trying to sketch the graph of f of x minus b. You can do that by shifting the graph of f right b units. F of x plus b, we can get that by shifting the graph of f left b units. Horizontal stretch. Suppose you're trying to sketch the graph of f of c times x. We can do that by horizontally stretching the graph of f by a factor of 1 over c. What does that mean? That basically means all the x coordinates multiplied by 1 over c. Now, is this a stretch or a compression? It depends on c. If c is greater than 1, so what you'll see is a horizontal compression. And if c is less than 1, then what you see is a horizontal stretch. Let's just keep it simple and call them all a horizontal stretch by a factor of 1 over c. And a horizontal reflection, you can get the graph of f of negative x by reflecting the graph of f in the y-axis. What's the proper order for horizontal transformation? It is opposite of the vertical transformation. First, we apply the horizontal shift, and then we apply the horizontal stretch and reflection in any order. Let's go back to our example and take a look at maybe our quadratic function. There we go, quadratic function. Let's add and subtract 2x. So let's take a look at f of x equals x minus 1 squared. Shifted to right 1 unit. X minus 3 squared, shifted right 3 units. X plus 2 squared, shifted left 2 units. Let's go back to our notes. Let's take a look at the first example. We would like to sketch the graph of f of 2x plus 1. 2 means a horizontal stretch. By half means all the x coordinates times half. Plus 1 means a horizontal shift to left 1 unit. In the proper order, we apply the shift first and then we apply the horizontal stretch. So let's do this step by step. I'm going to shift the graph of f to left 1 unit, left 1 unit, left 1 unit, and left 1 unit. I'll try to maintain the general shape of the graph. Now I'm going to apply the horizontal stretch by half. This means all the x coordinates times half. So this x coordinate currently negative 6 times half will become negative 3. The x coordinate here, negative 2 times half, will become negative 1. The x coordinate 3 here times half will become 1.5. Maintaining the general shape of the graph, we get the graph of g of x, which is f of 2x plus 1. Domain of g has changed. We applied horizontal transformations. We changed the x coordinates. The domain is currently negative 3 closed to 1.5 open. The range, however, did not change. Same as the range of f. Open negative 2 to 4 closed. Another example. what transformation do we need to apply to absolute value of x in order to get absolute value of 1 by 2 times x minus 3? There are two horizontal transformations here. One of them is a horizontal stretch by 1 over half, which is 2. So that means all the x coordinates times 2, and minus 3, which would be a horizontal shift to right 3 units. And the proper order, we apply the shift first, and then we apply the horizontal stretch. Next, we will talk about even and odd functions. An even function is a function whose graph has symmetry with respect to the y-axis. That means if you consider f of x and f of negative x, that they will be the same, will be equal. F of negative x equals f of x. The examples include f of x equals x squared. F of negative x is also equal to x squared. This is an example of an even function. The graph of f of x equals x squared clearly has symmetry with respect to the y-axis. Another example, f of x equals absolute value of x. F of negative x is also equal to absolute value of x. Graph of absolute value x clearly has symmetry with respect to the y-axis. Another group of functions which have symmetry, called odd functions, are the ones which have symmetry with respect to the origin. That means if you replace x with negative x, then the y-coordinate f of x will become opposite, will become negative of f of x. The examples would be f of x equals x cubed. F of negative x will be negative x to the power 3, which is negative x cubed. Clearly, f of negative x is equal to negative f of x. This is an example of an odd function, and the graph of f of x equals x cubed has symmetry with respect to the origin. Another example, f of x equals 1 over x. F of negative x would be 1 over negative x, which is basically negative 1 over x. F of negative x is equal to negative f of x. Graph of f of x equals 1 over x has symmetry with respect to the origin. How do we decide if a given function, using the formula, if it's even or odd, or it's neither, means it has no symmetry? We will try to decide about that by calculating f of negative x. If we can show that it's equal to f of x, then we conclude that it's even. If we can show that it's equal to negative f of x, then we conclude it's odd. And if neither, then there is no symmetry. So let's see. If I calculate f of negative x here, means I replace all x's with negative x, I'll have negative x squared minus 1 3 times negative x. That would be x squared minus 1 over negative 3x. It's easier to see what's going on if I move this negative sign to the front. X squared minus 1 over 3x. What is this? This is negative f of x, which means f is an odd function, and it has symmetry with respect to the origin. Let's look at another example. And g of x is square root of x squared plus 5 over absolute value of x minus 3. I will calculate g of negative x. I'll replace all x's with negative x. That would be square root of negative x squared plus 5 over absolute value of negative x minus 3. Negative x squared is the same as x squared. Absolute value of negative x is the same as absolute value of x. No change. This is equal to g of x, which means this is an even function. An even function has symmetry with respect to the vertical axis, or symmetry with respect to the y-axis. And so at this point, spent some time practicing using the textbook questions, exercises and problems, homework questions. If you have any questions, join my Zoom office hours and I will be able to help you with your questions. This is the end of our lecture.